Let's see here. Let's see. Actually, I want to start with this first. So this will be our last lesson on magnetic induction, and I'd like you to review on your own. Does anybody have your textbook with you? Can I borrow for a second?
Yes.
That's in the can. Okay.
Good, thank you.
I want to write down a couple of page numbers for you to review. Just to be sure you have this down, because understanding this will help you a lot. Let's see, review the magnetic field, the B field around the current carrying wire on page 107. This is in the EMM text, of course. Also review how the charged particle moves in a magnetic field, in a B field, page 109, and also the A field around the current carrying wire, in addition to the B field. And the relation between the two, that's on page 133. So review those things on your own. Make sure you understand those details really well, because all of this comes into play in terms of the induction in Chapter 4. You have to understand these really well so you can get all of the factors that go on in magnetic induction. Okay, so I'd like to begin today by reviewing the proper understanding of Faraday's law. Faraday's law is that the induced EMF is related to the time rate of change of the magnetic flux. Yes, ma'am.
Could you go back one slide?
Sorry. Keep up. All right.
Okay.
There you go. And of course, I'll make all of this available in the podium notes too. Okay, so the proper understanding of Faraday's law is expressed in terms of the time rate of change of the magnetic flux. The EMF induced in a secondary, for example, may depend upon how the magnetic flux changes in time, or does depend on how the magnetic flux changes in time. Now this is less fundamental than the Lorentz Force Law. So the Lorentz Force Law sorry. Oops. There we go. A field. 1 over C V cross B. Okay, the Lorentz force law has in it the two kinds of forces, the A dot and the V cross B force. This is more fundamental. He shows in the book, Dr. Rizzi shows in the book, how you can obtain the Faraday's law from the Lorentz force law in various different situations. And I wanted to go over the three different cases that we considered here so you can see the relationship between them. So we have, for example, if we have a wire carrying current and we have a secondary, so the wire carrying current, of course, is part of a larger circuit, right? And then we have a secondary that has no current in it. If we push the secondary towards the primary, we get an induced current in that. That was the first situation we considered. Or we could push the primary towards the secondary. That will induce a current in the secondary. And the third way is to change, like increase, for example, the current in the primary, make a stronger current flow in the primary. That will also induce a current in the secondary. As long as the current is increasing, you'll get an EMF in the secondary. Now, I'm going to go through this in terms of the Lorentz force law, but well, let's do that. Let's review how this works. So the second one, remember, the very first one is an example of the V cross B force, because there's a B field that's into the board here because of the wire. The current in the primary has a B field into the board into the paper, and it's weaker out here, right? There's a B field present both in the left leg of the rectangle and the right leg of the rectangle. Actually, it's also present in the top and bottom legs, okay? So when we have positive charges that are present in this piece of the wire, piece of the secondary there, we have a V cross B force, right? Because we're pushing on the charges in that way, so we have a velocity, and the V cross B causes an induced current and pushes down on these charges. So there's a force, a V cross B force, downward. Okay, but now you might ask, well, okay, now these guys, if there are charges over here, they're also moving with the same velocity. They also have a force, downward. But it's less. Why is it less?
It's further away.
Yeah, it's further away from the primary, so the B field is weaker at that location. Okay, so there's two forces acting contrary to each other, and the one that wins will be the larger force. And so now we do get a current that flows through the secondary in the counterclockwise direction. You might think, well, okay, why should it flow counterclockwise? Well, because the downward force on the left leg is stronger than the downward force on the right leg. So if we integrate F dot dl around the circuit, we calculate the amount of work done on a charge that moves around that loop in the counterclockwise direction. So this is counterclockwise. The net will be greater than 0 because there's a, if you look on the left-hand side here, there's a force downward and the charge is moving downward, so F dot dl is positive. The work done on the left leg is positive. On the right leg, though, the charge is moving in the opposite direction, opposite to the force. What I mean by opposite is I mean opposite to the force. So the work done on that stretch is negative, but it's not as strong. It's less magnitude. And so the net work done in moving all the way around is greater than 0, and the EMF is the work done divided by the charge. It's the work per charge. That's the EMF. Okay, Mr. McCone.
Are the charges moving counterclockwise because the left is larger
Yes.
than the right?
Correct. Yeah, that's right. Yes, sir.
So if the primary source was an infinite plate and it was perpendicular to the moving object, it would have a no induced charge?
Ooh, isn't that a cool idea? Okay, so Mr. McKenna is suggesting that we make the primary, instead of a wire, we make it a plate, an enormous plate, much bigger than the size of the secondary, and we get the secondary close to that plate, so we're far from the edges of the plate. And now let's try the same experiment. Now remember, how does the magnetic field strength fall off near a plate?
It doesn't.
Constant?
It doesn't. It's uniform in the vicinity of a plate where the current is flowing uniformly, right? You got to make sure that happens. It's uniformly flowing current, distributed uniformly over the plate, and that the plate is much larger than either the size of the secondary, and we got to get the secondary in close to the plate, so we've got the uniform field. Then we should see no induced current. That's nice. I never thought of that. That's pretty cool. Yeah. Might be interesting to try that. I mean, we have some constraints there. We have to create it. We have to generate a B field which is uniform over that region. So it's a little bit of a challenge, but we could do that. Or we could put it inside of a solenoid. That might be another way of doing it. Good idea. Okay, now the second case, it's an A dot effect, right? As we move the primary towards the secondary, the A is increasing now at this location. If A is increasing, what happens to the charges? They feel a current in the opposite direction. A is increasing, so now there's a force. What I meant to say is force. I said current. The charges experience a force in the opposite direction, opposing the change in A. And so we have a force on the left side. What about on the right side?
You also have a force. But it's
Also
smaller
have a
magnitude.
force. Also down. But it's less because A is smaller, and so A dot will also be smaller. Yeah. So you have to reassure yourself that in fact is true. I mean, just because A is smaller doesn't make A dot smaller. But in this case, if you look at it, A dot is in fact smaller on the right side. So again, we have a net force. Even though we have opposing forces, we still have a net force acting, and we still have positive work done if the charge flows counterclockwise. Remember, the force now is proportional to negative A dot. Okay, again, counterclockwise. Different cause, same effect. Okay, now in this third case, then again, the current is increasing, so A is increasing. Again, A dot causes a force in the downward direction in both legs, but it's weaker in the right leg than the left leg. So again, we have a net EMF going around the circuit. And so in all three cases, we can induce current flowing in the counterclockwise direction in the secondary. Okay. And we should feel, in doing this, when we push the secondary in the first case, when we push the secondary towards the primary, it should take some effort on our part. We should feel the repulsion because there's an induced current in the opposite direction, so it's repelled by the primary. So it should require us to push a little harder than if there were no magnetic field, no current. And the same is true for pushing the primary towards the secondary. That should take some effort for us. And in the third case, there's some resistance to increasing the current. So that's not a mechanical thing that you would feel, but the primary would be pushed away. Yes, sir?
So when you're doing the Lorentz Force Law for these,
yes,
when you take V, it's always from reference of the receiving component, so the secondary?
It's whatever the V is of the charges. That's right.
Yeah. Okay.
That's right. Of the charges in the
so
secondary.
You get the correct direction.
Correct. Yes, that's right. Okay, now, the Lorentz Force Law is consistent with all three of these. The Lorentz Force Law looks like it ought to be simpler, and in fact, you might be tempted to think, why don't we just deal with the Lorentz, back up, I said that wrong. The Faraday's law looks simpler because it encapsulates all of these in the same rule, and it looks like it ought to be simpler. And so it looks like you ought to always just rely on the Faraday's law. And he actually derives Faraday's law from the Lorentz Force Law. And Faraday's law is that case where we have we're looking at the time rate of change of the magnetic flux. So if we look at the first problem where we have the current in the primary and we're pushing the secondary towards the primary. Now the magnetic flux, we want to look at the magnetic field. And so we're adding up how much magnetic field goes through the area of the secondary, and it's weaker over here to the right. So it's not uniform. We have to do an integrate the magnetic field over this. And that would be the magnetic flux is then the integral over the area of the secondary of B dot ds, where S is the surface area element. So how much of the magnetic field flows through that secondary. And that will change in time, in this case, because we're pushing the secondary towards the primary. So the secondary, because the magnetic field is getting stronger as it gets closer to the primary, that means the magnetic field flux is going up. And that will induce an EMF in the opposite direction. Yeah. And it's exactly the same. Right? If you calculate it this way, you get the same result as what I just did above. All right, now in the other case, if we push the primary towards the secondary, again, we're looking at the flux coming through the secondary here, the magnetic flux. And that's also increasing now because the primary is getting closer, and so there's more magnetic field. And so it's penetrating through that loop, so increasing flux. And in the third case, we do that by just increasing the current in the primary. So now the magnetic field, of course, is getting stronger because the current that generates it is getting stronger. So it looks like we just have one rule. Why bother with two? If I can calculate it with one rule, why have two?
You lose the cause.
You lose the cause, right. The cause is obscured by this, by Faraday's law. As physicists, we want to know what's going on. We don't want to just calculate things. We want to know why it's doing what it's doing. We want to understand physically what is present. And the Lorentz Force Law captures physically what is going on. Faraday's law is less clear because it combines two effects, right? The same effect is what I mean is the two causes are combined here. And so it looks at the effect without looking at the cause. So you can calculate with Faraday's law in situations like this, but the reason for not doing it is, I mean, if you know what you're doing, you can calculate with Faraday's law, but there's the main reason for understanding the Lorentz Force Law is to understand the origin of the Faraday's law, right? The physical reason. Okay, now there's another reason which is less important, but which is also should be mentioned, and that is sometimes it's really tricky to use Faraday's law. For example, in the Faraday's disk. So in the Faraday's disk, we talked about this, and let's go over it again. We have a wheel, and we're going to, it's a metal wheel, a disk, and it's got a handle going through it's got an axle and a handle on it, God bless, so we can turn this thing, turn it this way, and we're going to put this inside of a magnetic field. So there's a magnetic field present, say, all around here, okay, including here. Okay, so we have lots of magnetic field. For simplicity, let's assume that the magnetic field is uniform. It's the same everywhere in space, all around this wheel. And we're turning the wheel, and now we find that if we attach a lead, we hook up a lead to the axle, and we hook up another lead to the rim, and we connect those, we find there's a current flowing through this thing. Now the challenge is if you try to use Faraday's law, you have to figure out, well, there's current flowing, so there must be a time rate of change of a magnetic flux. But naively, if you look at this disk, the area is not changing, and the magnetic field is not changing. The magnetic flux through that disk is not changing. So why should there be current flowing? Because it looks like if you just naively try to calculate using Faraday's law, you get a wrong result. There is current flowing through this. So you don't understand, now you get stuck, right? Because you don't know what you're doing anymore. Okay, but if you follow the charges, remember we have charges here. The charges are moving like this, right? They're on a merry-go-round and they're moving around. Okay, now there's a magnetic field present, there's a V cross B force, and which way is the force? V cross B will produce a force here to the left on these, so it will push the charges outward from the inside out to the rim, and that's why you get an EMF. And so you could calculate the EMF by calculating the work done along this path. Okay. He also shows in the text, so the Lorentz Force Law gets it. You don't have to, I mean, everything is contained in the Lorentz Force Law. You understand what's going on. Whereas the Faraday's Law is subject to a challenge here. He shows in the book actually how it is that you can use Faraday's Law correctly and get the right answer here, but it's kind of tricky, and you have to follow the charges and follow pieces of area and stuff to get this thing right. It's much more challenging. And there's another example that's in the homework. We didn't do this one, but it's in the back. It's in the problems at the end of the chapter, which is another example like this. It's got a piece of metal that's like pie-shaped, or it's kind of funny shape, and it's rocking in a magnetic field, and you hook up leads to it, and you can get current flowing through this thing. But again, it looks like there shouldn't be anything. According to the naive use of Faraday's Law, there shouldn't be any. And the homework problem is to demonstrate how Faraday's Law actually works. You just have to be really careful about how you use Faraday's Law. Okay, so this is a second reason for not using for not relying solely on Faraday's Law, because it gets really tricky in some situations to make it work. It does work, but you have to understand, and this is better in terms of understanding. The Lorentz Force Law will not run into this problem. Okay, but the main reason is, as I said at the beginning, physicists should always understand why it does what it does. Don't just calculate something, understand why. And the other thing that happens, of course, is in the second one, if you understand what's going on, when something goes wrong with the calculation, you know what to do about it, right? If you know that the Faraday's Law can be tricky, then if you get a calculation that disagrees with the experiment, you know how to resolve the problem, right? You go back to something more fundamental. Okay. Does that make sense? Okay. All right, so now let's look at just, In fact, I was thinking about this. This would make a nice test problem. Yes. Let's suppose we had a current carrying wire like this, and with current in it, and we're going to take a secondary, and I want to ignore end effects. I just want to look at what's going on. Forget about charge building up on the ends. Okay, I just want to look at the forces that are present here. If I take the secondary and I move it towards the primary, in fact, I'm going to have them offset vertically out of the page here, so they don't run into each other, they don't collide with each other. The secondary can move over the primary. So I want to look at what happens when this thing goes from here, gets closer, goes past. Okay, let's look at the whole story here. What goes on in this situation? So I want to look at the induced current in the secondary piece of wire there, and I want to look at the forces that result between the two wires as a result of this. And the whole time we have we try to maintain a fixed current in the primary. Mr. Picot.
Okay.
You were raising your hand, right?
Yes.
You weren't just stretching. Okay, good.
I think it would be like the V cross B thing.
Good.
And the V would be the same because the wire's uniformly moving.
Right.
And then the magnetic field would be, because I is constant.
Yes.
It would have the same magnitude, but it would be changing direction.
Correct. Well, it's not quite the same magnitude, right? Because you're getting closer to the wire or getting farther, so it's the distance from the wire is changing. So both the magnitude and direction of V is changing. So when the secondary is on the left, the B field is coming out, and when the secondary is on the right, the B field is going in. But it's much stronger close to the primary. Okay, good. So which way is the current flowing in the secondary?
I have a question.
Oh, it's a question.
So this is all happening in the same plane?
Well, almost. The secondary is just a little above the primary, so I can go past, right? They don't
Okay.
collide with each other. So there's an offset.
Okay.
Otherwise, it would have an infinite B field,
Mm-hmm.
right? I don't want to do that. So,
Okay.
or it would just, you'd have to figure out what's going to happen when the wires touch or something. So let's offset the secondary just a little bit above the plane of the figure so that it can move over the primary. Is there another question? Okay, so which direction is the current in the secondary? Let's start with the beginning over here.
Down.
It's down, right, it's down. V cross B, right? Can you do that? Make sure, like I say, you're going to, with these problems, you risk breaking an arm. So it's going down, and then as it gets closer, it's stronger because the B field is getting stronger. V is the same, but B is getting stronger. Okay, now on the other side, it's going to flip, right? But then, okay, all right.
Shouldn't it stay down? Because now,
Shouldn't it stay down?
yes, because our velocity also changed reference to where the B field's originating.
No, the V is in the same direction. V is the same all the way across. This is V. V is to the right, and the magnitude is the same by construction. So V is the same. The only thing that's changed is B. And when it goes past, now B is flipped over downward, so the V cross B is now up. Okay, how about the yes, sir, Mr. Picot.
When it moves like right across, would the B field not be in this direction?
Yeah, that's right. Yeah, so when the secondary is right over top of the primary, which way is the B field pointing?
Along the velocity.
Yeah, that's right. It's parallel to V, so there's no Lorentz force when it's right over the primary. So there must be, we could work a little harder here at figuring out what the transition is, but that would involve, the detail of the secondary and the primary being close to each other. So we could work that out. Okay, now the forces between the wires.
It's always working against movement.
Always works against the movement, yeah. So in the left case, when it's approaching the primary, is pushing them apart, but when it gets on the other side, now the currents are in the same direction, it's attractive, which again tries to keep it from moving to the right. So on this side it's repulsive. Hello. Repulsive. On this side it's attractive. Right? Well, that sounds like the magnet in the copper pipe, remember? And it was always resisting the motion of the magnet down the pipe. It's the same thing again, just different geometry. Except this is a V cross B, not an A dot, because we're moving the secondary here. In the other case, the secondary, the copper pipe, was stationary. So, okay, so you could do the same exercise, saying I'm going to hold the secondary fixed and I'm going to move the primary. So we're going to move it in the opposite direction. Let's go that way. And so we push the primary now to the left, starting off at the right. And so we go through the same exercise, but it's an A dot effect. It's the A dot cause now. So we can calculate, and the same thing here in the secondary. We're inducing a current in the secondary because the A field is increasing when the primary is over to the right. So the A field is increasing, so the current in the secondary is down, right? And then when it's on the other side, the current in the secondary is up. You go through the same sequence again, it's just using a dot. Okay? All right, that's kind of a nice little exercise. And again, to help go over the pages that I had for you to review, again, make sure you get all of these signs correct. If we change the direction of the current in the primary, what's going to happen?
The induced current's going to change.
The direction of the induced current will also flip, but the repulsive and attractive interactions between the wires will be the same. Okay. So make sure you get all of these signs right and all these directions, the cross products and the A dots and all this stuff. Make sure you get all of that right so you can get all of these things right. I mean, notice how rich this is. This is amazing. I mean, we went from gravity, which, for really small bodies just always attracts. Then we went to electric forces, which could attract or repel, and now we've got this really kind of rich behavior. It depends on the direction, of the impetus and the field and all that stuff. I mean, it's just amazing how rich this has become. Okay, yes, sir.
Are
Mr. Head.
electric or magnetic fields generally stronger?
Yeah, very good question. So electric fields are generally stronger. The effect of an electric field is generally stronger. Is that what your question is? The effect is stronger, not the field itself? Okay. In the Lorentz Force Law, you can see why that is. Because, well, let's go down here. Let's do it this way. So in one case, if we have an electric field, this would be the force due to an electric field. Or if we had a particle with impetus moving in a magnetic field, this would be the force on this. In CGS units, the electric and magnetic fields, the E field and the B field, have the same dimensionality. So if E and B are of comparable strength, E will have a stronger effect because the velocity is always less than the speed of light, and usually much less than the speed of light. Around doing things here on the tabletop, the speed is usually much less than the speed of light, or some fraction of it. Okay, so usually you're more concerned if there are bare charges present. You're more concerned with the electric field, the effects of the electric field. All right, and the inductive effects are only going to be visible if there are no net charges floating around, because the net charges would kind of obscure the inductive effects, for example, or magnetic effects. So the current carrying wire needs to be neutral, has no net charge on it, so that you could see the magnetic effects. Otherwise, you're going to see electric effects and magnetic effects, and the electric effects are going to dominate. Okay, good question. Okay, now let's see here. I wanted to show you something else here. Oh, Mr. Picot.
It's kind of a random question, but
Random.
in like a wire, like an electrical wire,
Yeah.
it would be hanging.
Yeah.
If there's like current going through that, would there be a magnetic field if you were up there near it.
So if you have a wire with current flowing in the wire, and it's just a length of wire with ends, and you push current through that, then you'd have charge building up on both ends. So you'd see both electric and magnetic fields generated by that. Did that answer your question?
Kind of.
Kind of. Okay, you got something you're thinking about. I'm not sure what it is.
Like the power lines, because there's not really like an end.
Yeah.
I mean, there is an end, but it's like a long ways away.
Yeah, okay. So a power line, you should see a magnetic field around the power line.
Would there also be an electric field? Because it's insulated by the rubber with the electric field.
Well, if it's a coaxial construction, depends on the construction. If it's coaxial, then, well, usually no. Usually you don't see an electric field around it unless there's something else going on. If it's just a wire, straight wire, then you don't see an electric field, usually. Okay, now we had here, oh, I got it. Yeah, okay. We had here a, in the demonstration we had an aluminum trough. It was a V-shaped thing, and we put just a steel marble and it just rolled down. Then we put a magnetic marble and it slowed down and sped up, slowed down, sped up. It moved kind of erratically. So that's an example of magnetic induction and these forces that are present between the induced currents and the primary. Now the magnet we can think of as a, God bless, as a primary current loop, all right, and then it's put near a metal surface. So I went through the exercise of looking at. So let me back up and show you the geometry here. So I'm going to put a magnetic sphere on a metal plate. And the magnetic sphere, in the first calculation, I'm going to have the pole coming straight out of the board here, and the sphere is going to roll this way. So the pole stays fixed, and it rolls, moving to the right, like that. And I want to calculate the induced current here. Well, you know how to calculate an A field. Remember, the A field is M cross R hat over R squared. Right? You did that. So you can calculate the A field inside of the plate, and then take the time derivative, get the A dot, and look at the current distribution underneath the plate, inside the plate, because of that rolling magnet, like that. So that's the first thing I want to show you here. So here's the, I'm looking down on the plate here, so the top view. Here's the sphere, here's the north and south poles like this, and the thing is rolling to the right, like that. And now I'm going to look down onto the plate, and that's a picture of the A field right underneath the magnet. The magnet is north and south pole are arranged vertically, like this. And that's the A field, and this is the time derivative of the A field. So this is a plot of the currents produced in the plate. So this is now a flat plate, not a V-notch thing. Flat plate is complicated enough, so let's just do a flat plate. So you can see the current in the moving magnet, below the moving magnet in the metal plate, is flowing around like that. It's a little more complicated because there's actually a component of the current perpendicular to the surface. So charge is building up on the surface of the metal while this thing is moving. And so that's what the charge buildup looks like also. Okay, so now let me show you an animation of what the current looks like. Hello? Didn't do it? Oh, it's still working on it. Oh, I see. Excuse me. I need to do this. Okay, there we go. So now the magnet's rolling from the bottom to the top. The poles are arranged left to right. Okay, and then as the thing rolls, the current underneath the this is with the, I'm sorry, this is the one reason I'm getting confused is this is the one with the where the poles are rolling in the opposite direction. Let's go back to this one. Here we go. Okay, excuse me. I'm getting confused here because I had two notebooks. Okay, here it is. Here's the current under the rolling magnet. Okay, so this current is flowing differently than what I said. I was showing you the wrong one. This is the one where the poles are horizontal here, north and south arranged horizontal, and you can see the current flowing. It actually flows down into the plate and back up again, which you can see in this cross-sectional view. You can see the current flows down into the plate and then back up as the magnet rolls on top of the plate. So you can get all of this simply by looking carefully at the A field and taking the time derivative and just plotting. Okay, it's really not complicated. This other one that I was showing you, I should have shown you second. This is what happens if you take the magnet now and change the geometry a little bit so that the magnet is rolling and the poles are changing. So now let's suppose that we had it so that the poles started off north and south like this, but the thing is rolling this way. So after some time, the north pole is pointing down, and then after some time later, the north pole is over here, and then after some time later, the north pole is like this. So it's rolling, and the poles are changing too. It's a more complicated arrangement, but it's very easy. That's what I was showing you here. This is actually what the current, looking down on the magnet, that's what the current distribution in the plate looks like, the induced current.
You mean to change the screen?
Excuse me. Thank you. Yes, that would help. Can't you see what I see? There it is. There's the induced current now in this case. And this is what the current looks like down into the plate, the cross section. So you can see, again, the induced current is flowing down into the plate, back up. Okay. You can get all of this simply by looking at the A field and taking the time derivative of the A field. And then if you have a nice program like Mathematica, you can make these plots. Okay. Okay, so that's what was going on with the magnet rolling on the plate, or on the V notch. It was inducing current in the aluminum. Then there's a repulsive effect, or attractive, right, depending on how things are moving. And it depends on how the poles are oriented in the rolling. So if we could get the poles lined up in a nice way, it would roll steadily down. But if the pole is at some funny angle so that it's doing this when it rolls down, then it's going to speed up and slow down and speed up and slow down. Okay, so I have some interesting little demos here. Let's go to the document camera here. So you can't really see it very well in the document camera, or even very easily out in the classroom here, but here's some horseshoe magnets, and then there's some coils here, been wrapped quite a bit. And I'm left-handed, so I'm right-handed, so I can't do this as well this way. But you can see a little bit of current flowing in this. It's actually not a whole lot, okay? But so I'm changing the motion that I generate with my arm. So I have to do work on this thing, and that comes out as current flowing through the light bulb, lights up. So I'm dissipating the work done by me through the resistor, and it's actually a little easier if I unscrew the light bulb. It's easier to do this. It's not as hard to move it. So I can actually feel the amount of work, increased work required to light the bulb. It's kind of interesting. Of course, I can do this backwards. I can take, first, I can do it this way. So I can use hydroelectric. This is hydroelectric power works. Of course, you get the water to do this, make these things move. So you're moving a coil inside of a fixed magnetic field. Okay. The other way you could do it, of course, you could work this backwards. put current into it and make it move, which is a motor, right? So I don't have any motors to show you here, but I do have some things. So I have a volunteer. I need a volunteer. Somebody. Mr. McKenna has volunteered before, so somebody else. This is a little handheld generator. Okay, crank that.
Restriction.
I don't think it matters. Okay, crank it the other way. All right, that works pretty good, doesn't it? Okay, now I have two of them. Actually, this is going to be what I said I didn't have. Okay. All right, crank. Okay, here, let's do it. All right, crank. Now go the other way. Yeah, it goes the other way. Okay, hold on. No, I still got more stuff for you to do. Here's a capacitor. Okay, I'm going to charge up a capacitor. Okay, crank. All right, let go. What's going on?
The capacitor is discharging.
Yeah, the capacitor is discharging, so it went from a generator to a motor, right? You discharge the capacitor. Okay. Cool. Crank it up again. Let's see if I can get this to work. All right, so we should have a okay. So it's to demonstrate how the capacitor works, right? It's not doing anything, right? But hook it up again. So the capacitor stores the charge, right? It's a battery in that sense. And if I put a light bulb on this, let's see if I can do it without losing the charge. Capacitor. No. Here we go. No, it's not working. Why isn't that working? So they discharge the capacitor. Should have discharged through the light bulb. Should have been able to see that work. Oh, I was gonna. Okay.
See if it still had.
Yeah, I was gonna. Sorry, I wasn't clear what I wanted you to do. All right, good. Thank you very much. That's kind of fun. Here, I'm going to pass these out. You can play with these. Yeah, I can charge the capacitor, or you can do the light bulb if you want to use the light bulb.